Hello, everybody. Thank you for being here. It's a pleasure. Priya and I are really excited to talk smart case routing systems with you today. It's a combination of some of the better techniques that we've encountered, the better approaches, the best tools, and also lessons we've learned from building case routing systems and natural language processing through the years at SpringML. Let me look at the agenda here. We're going to start by introducing ourselves, SpringML and case routing, briefly. Then we're going to tackle the meat of the matter, the three main models that build this smart case routing system. And finally, we'll open it up for questions. And we'll also be around afterwards if you have additional questions. So let's present ourselves. Do you want to start, Priya?
Yes, sure. Hi, everyone. I'm Priya Dwivedi. I'm a data scientist at SpringML. I've been at SpringML for about 6 months. Prior to joining SpringML, I worked for Capital One for about 10 years. I'm very passionate about deep learning, and I've been working through it for the last 3 years. I also write blogs very frequently, and you can find me on Medium.
Thank you. My name is Manuel Amunatigi, and I'm also a data scientist. I'm the VP of Data Science at SpringML, and I've been at SpringML practically since the beginning, I think a few months shy since the company was created about three years ago. And I also am, so prior to that, I was a data scientist in healthcare for 4 years, and prior to that, a quantitative developer on Wall Street for 6 years. And I'm very passionate and interested about applied data science. I like to see how we take all these models that are coming our way every day and see how we can apply them to make our lives, everyday life, easier, right? So, of course, curing cancer would be great, right? But it's not an easy thing to tackle. But like case routing, these kind of things, we have the tools today to do it and to do it well. So that's very exciting. So briefly about SpringML, we're a company that brings AI and machine learning to companies who either don't have the staff, the department, the know-how, or need extra hands. And we will kind of take a step back with them, look at what they're trying to do, look at their data, if it can be achieved, and then dive in with them as a team so that we work in tandem and that they have a sense of ownership, and then they can take it on, they can extend it, and they can sell it internally if need be. And we're also happy to form longer-term relationships. I mentioned that we've built quite a few case routing systems, and that's true. Over the years, we've built them, and what's interesting about case routing and natural language processing in general is that it has evolved enormously. What we're going to present today is very different than what we started. Actually, there's probably very little that intersects. We've done a lot of case routing demos internally. We've done them for Google, and we've also partnered with Google for other customers. The biggest customer we've worked with is CBRE. It's a very large commercial real estate company. They're all around the world, and you can imagine the flurries of cases going back and forth, issues, questions, comments. So you could have on one end, please change in this country, change a light bulb here. There you could have, there's a great investment opportunity there. Or, here there's a building that's flooded. We need, the basement is flooded. We need, to call the maintenance crew. So all these things go back and forth. This is a very large company. So automating case routing for companies of that size, but even smaller companies, is a huge win. That's what we're going to talk about today. So that we're all on the same page, what is case routing? So case routing is whenever you have a department, a team, or even a single person that is in charge of taking either external queries or questions or internal ones and routing them, case routing, right? Routing them to where they need to go. In some cases, they can even answer them, right? I don't know, show of hands, who's been on call with their job? Yeah, I was on call when I was in healthcare. I was on call, and it was really a tough job, very stressful. Because I remember, healthcare never sleeps. Machines go down on the weekend or at night, and I didn't know who to turn to, where to get help. The people I would normally ask help, they were either sleeping or playing golf, right? So it was very stressful, and that's why I have a personal agenda to work on this, to fix this issue. And why would you want to automate this? Well, the obvious reasons why you're removing that middle layer, like the people on call like me who don't want to be on call, you're removing that, and the customer or the client, or the employee who has a question, they know that's going to go to the right department immediately. You get 24/7 support. You can handle multiple languages, right? We modeled this in English, but you could very well model in any language you want. So once you have one language down, it's just a question of getting enough historical data to model other languages. You can do auto reply, right? Very simple auto reply, like somebody saying, when is the office open? And you say, oh, this country has a national holiday. Try this, this date, right? These are easy wins. You could automate that. And more important, I think, is the centralized digital trail. You're going to start getting a warehouse of all your queries, all your questions, and so who's asking what type of question, where are their problems, what department tackles those answers, which one are struggling to answer those questions. All that is gold for a company, right? You can really learn a lot about your company, about what's going on with your and learning about your customers as well. So these are the three main models that we're going to talk about, but basically the brains behind what we're going to present. There's going to be a convolutional neural network that's going to do the predicting of what department to route a case to. There is the Google Language API that we're going to leverage as much information as we can from there to get additional information. And finally, finding similar cases. So you got a case that came in, you want to know what is a similar case and how was it resolved. That's great hints for somebody who's handling the caseload. And as a high-level architecture, before we dive into the CNNs, this is what we've built in the past, and this is what we would build today too. You have the incoming case that comes in, and you have the app engine. So the app engine is a serverless instance in the cloud. It's a great tool, a great type of instance, compute engine for this type of project, especially if you have cyclical caseloads, right? So if you have more cases during the year, these things will size automatically, will balance, will scale, and you pay only for what you use. It's also kind of the choreographer, the manager of the data. It will do some data cleaning, pass it to the cloud MLE, the mounted machine learning engine in the cloud, which is hosting our convolutional neural network. And Priya will talk more about the data set, but it's about financial consumer complaints, right? We're using an open source data set. And it can route it into one of 7 departments: consumer loan, vehicle loan, bank account, student loan, mortgage, credit card, or payday loan. So these departments are all related and all within the financial industry. And so the CNN will tell you what department to route it to. So now we know where to route it. The app engine will then also pass that information to the language API, where we're going to get all sorts of information we can, like sentiment. We'll know if it's the tone of the case, things like the organization involves. And now we can populate that information in our case report. And we're also going to query BigQuery with a huge bottomless data warehouse, where I was reading you could query like 35 billion rows in seconds with no indexes. So a very powerful tool, perfect for storing all of your knowledge base, all your cases. And here we're going to pull similar cases. And the end product for the demo is this smart report, we call it, right? So it will tell you what the complaint is, give you some hints about what's going on there, and some suggestions of how to resolve it. So this is for the demo, right? Most of the cases, we would feed this directly to the customer's CRM, right? They probably have a tool already, so either a REST point or an API, right? But for the sake of the demo, we wanted something that was visual. And I'm going to pass it to Priya, who's going to talk about the CNNs.
Thanks, Manuel. So I'm going to talk about how we build a convolutional neural network in TensorFlow to do the case routing. So before I start, by show of hands, can I know how many of you have built any kind of model in TensorFlow before? OK, that's a lot. That's really good to know. I've kept the talk here high level, but if you have any specific questions, feel free to stop me after the talk. So the first thing I want to talk about is the data set that we use to build this model. Consumer Financial Protection Bureau in the US has a publicly available data set of 274,000 consumer complaints across many different products like mortgage, credit cards, student loans, etc. When a consumer complains to CFPB, they have the option of making their complaint public. And when they decide to do that, any sensitive information like their names or amounts or dates are anonymized, and this data is publicly available. We think this is a really good data set for deep learning because it's pretty big. There's a huge variety here. It uses natural language. And what I mean by that is if you actually read through the complaints, you'll see that some complaints are very long, some are short, there are spelling mistakes, some consumers repeat themselves. So it's perfect to use that for deep learning. I also feel that the database is very rich in financial terms, so it's possible to actually use this data set for other use cases like routing customer service calls. So now that we have the data set, you can think of this data set as individual complaints, and complaints can be long or short. So I've taken a sample complaint here that says, you declined my transaction when I was shopping. And this is all words. but neural networks love numbers and maths, so we do preprocessing that converts these sentences into numbers. The first thing we do is we break the sentence into individual words, and so that would be you, decline, my, transaction, etc. And then we map these words into integers. So we could say that you corresponds to 23 and decline corresponds to 45 and so on. And this can be arbitrary. You can choose any of them. You just need to save this mapping for later. So if you want to convert the integers back to words, you can do that. So now we have our complaints represented as integers. So when we feed them into the neural network, we have to assign a tensor to hold them, and it's TensorFlow likes the tensors to be fixed size, so you can specify them in advance. So this means that it would like all complaints to be of the same length, but in your data set, different complaints can be different lengths. So to solve this, we choose a length, and then we make sure everything is that length. So if it's longer than that, we truncate it. If it's shorter than that, then we pad it. So let's say in this hypothetical example, we want everything to be 12 words long. So this is 4 short, so we add 4 zeros at the end, which correspond to a pad token in the model. But just for reference, the actual data set was much longer, so the complaints were padded to 600 words. Okay, so awesome. And so after this point, we have our data set is all complaints of same length, all of them represented by integers. But if you think about it, all these integers are unique. So we have all words represented uniquely, but that's not really how our language is. Words are not unique. Words are related to each other. Some words are synonyms, some are antonyms. Some words are very likely to be in similar contexts. For example, like king and queen are very likely to be talked about in the same context, much more so than king and AI, right? So to get over that, or to give the model our understanding of English language, we convert each word into a vector. And this can be a vector of any size. We ended up using a 128-dimensional vector. And so what happens is that words that are similar or are likely to occur in similar contexts have word vectors that are closer to each other in the vector space. And so this allows us to give the model understanding of semantics. So to train these word vectors, we can use 2 techniques. We can train these word vectors as part of training the neural network. So we initialize them randomly, and then we use backpropagation to train them as we build the model. And that's what we did in this case. And this allows the vectors to have understanding of financial terms. The other way is that you can actually use pre-trained word vectors, and these are available on the internet. I think Glove is a good source of these pre-trained vectors. And these pre-trained vectors have been trained on huge corpus of English language like Wikipedia and stuff, so they are also good at generally understanding what context words are used in. So Manuel will later show a use case where he used the pre-trained word vectors. Okay, so now we have, we took our complaint and we converted everything into numbers, so we're good to use a neural network. So in this case, we built a CNN for text classification. I think a lot of you might have heard of CNNs. They have been quite popular in computer vision. They have been used very successfully on images for detection, tracking, classification, etc. But more recently, CNNs have actually been used very successfully for text classification as well. And this might sound a little bit unintuitive. So part of the goal of this slide for me is to actually explain to you the architecture on a high level, and also give some intuition around why this actually works. So maybe let's start with a small sentence here. I like this movie very much. So this is 7 words, and each word is represented by a 5-dimensional word vector. So you can think of this as a 7x5 matrix, and at this point you can see that it's somehow like an image because it becomes 2D. And then we choose different filters. So we choose filters of size 2 words, 3 words, and 4 words, and they're represented by different colors here. These filters will do the convolution operation on the sentence. One way of thinking about this convolution operation is, so filter of 2 words will look at 2 adjacent words, 3 words will look at 3 words, and then 4 would look at 4. And so this is kind of like a bag of words. So the neural network is trying to look at adjacent words and trying to extract meaning from the sentence. And then it creates these feature maps, which are these 1-dimensional vectors that have summarized everything. And you can see them as different vectors of different colors here. And then finally, since all of these feature maps are different length, to actually use them in the neural network. We do sort of like a hacky fix where we do a 1D max pooling. We take the maximum value from each of these feature maps and combine them to create this colored vector at the end. So the way I think of all of this operation is the neural network has, or the CNN has gone over the sentence and extracted all the relevant information and combined that into that colored vector, which is the output from this stage. Okay, so I want to summarize the model once more before I move on. So we started with raw text of complaints. We did pre-processing that converted the text into integers. Then we converted all the word integers into word vectors. We built a CNN. In our actual CNN, we use 4 different filter sizes of 2 words, 3 words, 4 words, and 5 words. We do the concatenation. And then the final layer in the model is a fully connected layer with sigmoid activation. And what this does is it assigns, basically assigns each complaint into one of the 7 departments, assigning them different probabilities. And we can just pick the department with the highest probability as the prediction from the model. So as you can see, this is a relatively simple architecture, and it's amazing, how well this works. So we were able to get 85% accuracy in correctly predicting department on the test set, which is the set that the model wasn't exposed to at the time of training. Some of other big benefits here were the model is actually quite quick to train. So it took only about 15 minutes of training time on a single GPU. Since it's so quick to train, it's very easy to do tuning of hyperparameters or testing out different architectures. It runs pretty fast at inference time as well, so we're able to use a CPU at inference time, and that's what we will show in the demo as well right now. It can also be retrained periodically. So let's say you roll out with this model and you use it for 3 months and you collect new real data in the field. You can easily plug that back in and retrain the model. And then finally, I think a more subtle but actually pretty important point is because this model uses deep learning, you don't really need to do any complex feature engineering. The model itself extracts features, which means that you don't need to be an expert in financial services, and you also don't need to be an NLP expert to use this. This, in my opinion, makes deep learning very versatile, where same architecture can be applied on different problems in different domains, in legal, in financial services, in wherever you want to apply them. Okay, so we have talked a lot about the model, so now I want to actually do a demo of it. Let's see if I can switch screens. Okay, this is awesome. So what we did is we designed a web demo. So this demo allows us to interact with the model more easily. So in this first page of the demo, we have the customer's name, phone number, and address, which is arbitrary at this point because the actual data had this information anonymized. And then in this section right here is where we can put in a complaint, and then when we run it, this complaint is run against the CNN at the back. So the complaint that I've chosen is an interesting one. It says, I'm in the process of refinancing with Quicken Loans. It's been over 45 days, and I still don't have a closing date. They keep giving me the runaround, and it's been nothing but a headache. So what I personally find interesting about this complaint is there is no mention of any department here. And it's actually a very small complaint as well. So if you're not familiar with the financial services domain, it might be hard for you to know what product is being talked about here. And that, I think, is the whole benefit of deep learning, is just by looking at a whole bunch of complaints, it has understood what are the key terms involved with each product, and it's then able to use that. So now when I hit submit, the neural network runs in the backend and actually assigns this to the mortgage department, which is correct. So besides actually predicting the department, which is what the case routing would help with, we also have here what we call the smart report. So this report has a lot of interesting insights. So from the text in the complaint, we are able to create this word cloud, which has the key words in the complaint. We're also able to give a sentiment index, sentiment score to this complaint. We can extract organizations and categories that are being talked about, as well as we are able to look into our historical database for other similar complaints and present that to the agent who's actually working this complaint. And that can be pretty useful, right? So if you're working on this complaint, you might want to know what was done in the past, and you can apply a similar resolution. So in the next part of this presentation, we want to go and talk about how we actually created this smart report. Let me switch back. OK, so I'm going to now talk about how we use the Google Language API. So before I start, like by show of hands, can I know how many of you have used the Google Language API before? OK, that's good to know. So those of you who haven't, I would actually encourage you to try it out. It's pretty simple to use. So there is the homepage for the natural language API has sort of a section where you can use it easily. You don't really need to code in Python to do this. So that's what I want to do now is I want to actually showcase the web page where you can use the language API. So this is, I clicked right into and went into the natural language API homepage. And within here, there is the option to try the API. So I picked a sample sentence that says, ABC Bank has associated my number with someone else's delinquent account. They're calling me every hour and will not remove my number from the other person's account. So this person is clearly stressed. So when I hit analyze, essentially what would happen is that the language API would go and extract information and share that with me across 4 tabs. So there's entities, sentiment, syntax, and categories. The entities portion of the API looks at things like, hey, what's an organization, what's a person, what's an event, and stuff like that, and presents that information. The sentiment tab gives me a sentiment score for the entire text, as well as for each individual sentence. So it has correctly assigned this sentence a slightly negative sentiment, which is true. And then for each individual sentences, there is a sentiment score. What I find very, very interesting here is that if you look at the second sentence, which says, they're calling me every hour and will not remove my number from the other person's account, there's actually no real big negative word here. But the model has correctly understood that the overall sentiment here is pretty negative. And I would have actually done the same. I would have assigned this sentence a pretty negative sentiment score. So the API also has very, very rich information about syntax. So this has things like part of speech, like what verbs are noun, verbs, adverbs, etc. It also has dependency map, which can show you visually how words are related to each other. So you can use this to very quickly understand what are the verbs in your sentence and then do analysis after that. And then finally, it also has categories. So for us, it's very generic. It says these complaints are related to financial services and banking, which is true. But I think this feature can be very useful if your data set has complaints of many different types. And then it can actually tell you what the relevant categories are quite accurately and would be useful. OK, so now I want to hand it back over to Manuel, who will walk you through how we use the language API in our demo.
Thank you, Priya. So Priya gave us a good overview of what the Google Language API is all about. And I want to kind of dive a little bit deeper into how we used it in the Smart Report. It's a very powerful tool. I think these are pre-trained models in the cloud. So whenever you can use anything that's pre-trained, whether in image modeling, transfer learning, in using pre-trained word vectors and NLP, or things like tools like these pre-trained models, Google offers many of them, not just a language. There's vision, there's video, there's translation, there's transcription, all sorts of really cool tools. Whenever you can push that work onto other people who specialize on that, it's a win. That allows you to focus, you and your team, on the use case, on the business use case, and leverage these tools that work really well and are probably harder for us to replicate as well. And it frees up a lot of time on our end. So the Smart Case report, this portion of the report is fueled, is powered by the language API. And I'm going to walk you through a few things. So the word cloud is interesting, right? It's been used a lot in educational tools, but it's also very powerful in terms of highlighting word frequencies, which words are used the most. It's very visual. You don't have to worry too much about the way it's presented. It's going to present it for you. It'll show the largest words, in a larger font, and everything else, smaller. But it doesn't have to be frequency. It can be anything you want, right? You can program this. You could do, for example, part of speech, which Priya was showing us, like the action verbs. I want, I need, that would be also useful in terms of quickly figuring out what a piece of text is about. They're very easy to implement. You can program them in all sorts of languages, through REST calls, through Python. It's just a call to the API. And, oh, and also the sentiment index, right? It's a number between, I think, -1 and 1, right? And here we present it in a linear scale with emoticons from very unhappy to very happy. You know, in a fraction of a second, you quickly know the tone of the email. So very powerful, especially if you're doing customer service. The topics, so those are also referred to as categories. There is a category and a subcategory. Currently, there's, I think last time I read, about 700 categories it supports. In the financial world, it does a really good job at differentiating it, because as you saw, our 7 departments are pretty closely related. It still tells the difference between all sorts of things, very powerful. And a nice thing about using these cloud-based pre-trained models is it's 700 right now. And you can go to sleep, and when you wake up in the morning, suddenly it's 1,000 categories or 10,000 categories, right? So you automatically benefit from better pre-trained model without having to worry about it, because you're just calling the API. The organization is also really cool. You'll pull all sorts of the entities. It can pull famous locations. It can, I think, locations. In this case, organizations. So really smart to pull these kind of things, and quickly tell the person, the agent that's taking care of this, who are the major players in this complaint. And now I want to talk about pulling similar complaints that were resolved in the past. So there are different ways you can approach this problem. We thought we had a pretty clever one here. And the idea is that you have an incoming case, an incoming complaint for this data set, and you want to know what have other agents done in the past and how have they resolved it, right? So not only is that going to be a lot of help for the agent, it's also a step closer to doing auto replies, right? Once you know how this works well, you can determine, well, I think I can the machine learning can handle this automatically. Let's just fire off a reply. So you have this original complaint that comes. Let's imagine it has 20 words, right? And we want to, so it's hard to, you have these 20 words, it's hard to kind of fish in the entire knowledge base of historical complaints that we've dealt with in the past and finding a similar one, right? So what we're going to do is we're going to use pre-trained word-embedded vectors to boost the vocabulary, right? So what is, Priya talked a bit about it. What is pre-trained word-embedded vectors? So GloVe is a really popular one. They have taken either Wikipedia as a corpus of the English language or even Common Crawl, which is like a certain percentage of the entire internet, and modeled it to figure out exactly how each word relates to each other word. So in the end, it's very complex modeling, so that's why we're very happy somebody else did it for us. And in the end, you have a matrix with all the most commonly spoken English words and a long array of numbers. And these numbers for each word represents how one word relates to another. And that's how you can get the king to queen is, man to woman. It understands that there's basically a mathematical underlying to the English language that's captured in these pre-trained word vectors. And if anybody has worked with Word2Vec and has pre-trained their own corpuses, it's not easy. It takes a lot of time. You got to have the right equipment, and you got to tune it correctly, right? Otherwise, you got to go back and do everything. I did that a lot in healthcare, and it was a lot of work, and we didn't have GPUs, so it was like sometimes a week to 2 weeks of work, right? And just to find out that you made a mistake and you had to do it again, very frustrating. So this is phenomenal that they make these available. The GloVe is from Stanford. I think Stanford and GloVe are working together. Stanford is maintaining the GloVe data sets, and they're open source. Anybody can use them. So what we're doing, we're basically taking every word of that original complaint. Let's pretend there's 20 words. And we'll zoom into one word, the word transaction. So then you can say, using this pre-trained matrix, find me all the words that are close to the word transaction. And because you have this complex matrix that represents how each word relates to every other word, you can use any distance metric you want. Euclidean distance, cosine distance, it doesn't matter. And you basically have created an electronic, very powerful thesaurus, right? So instead of having just the word transaction, you can boost it to buying, business, contract, agreement, or even hundreds of words. So you do that for all your important words, not just, you ignore your stop words, all your important words. So you take that case that has 20 words originally, now you can have 10,000 words, right? And you can go fishing, basically a big bag of words, and you can go fishing into your knowledge base and finding the most related, the closely related cases to bring to the surface. Of course, you got to weigh the words, you got to do a little normalization, otherwise the very large historical cases would take precedence, and you don't want that, right? So there's a little bit more work involved, but that's the overall idea. So then you basically, I'm going to repeat what I just said. You're going to go with that huge bag of words. Instead of 20, now it's 1,000, and pull similar cases. So that has 3 distinct advantages that are pretty powerful. For starters, you can now find cases, you can now find historical cases that don't intersect, have no word at all intersecting with your original, the new incoming case, right? Because you buffered that with a new vocabulary, they could have no word in common, and you can still pull them out. The second one is there's no training on our end. We're not modeling this on our end because we're kind of piggybacking on the pre-trained word vectors, right? So all that work is pushed on to somebody else. We don't have to do any pre-training. That saves us a lot of time. And the third advantage, which is related to this, is that because we're not doing any pre-training, we don't have to waste any of our own knowledge-based data, our own historical case data for training. We can then use the entire corpus to find similar complaints. You can, going all the way from the first complaint ever entered in your data warehouse to the one that maybe it was resolved 2 seconds ago. If it's similar, we can find it and we can pull it. So you have access to your entire corpus. That's pretty powerful. I'm going to do a demo as well. So I have a simple case here. I'm having issues with my bank. I have been late on 2 payments, and I can't get in touch with anybody to work on some kind of repayment plan. I'll be upset if this ends up hurting my credit score. So I'll run this. So the top of the, right, so it's saying credit reporting, which is correct, right? That sounds about right. The original case is there. You have, you know, the information from whom that came from, and you have the sentiment index. So more or less correct. It's slightly negative to neutral, and you have, you know, the word cloud says issues with the bank, and even the word late. So off the bat, you know exactly what the case is. This becomes way more useful if the case is very long, right? Because you'll really see things pop out. It says, you know, topic is finance, and I purposely didn't put a bank name in there, so it just says bank as the organization. So, you know, that's acceptable here. And then we see the similar complaints, right? So there are complaints that are extremely long, and what I like here is that it's not pulling anything too large. So we know that there is some, you know, it is kind of, you know, looking at not only the similar words, but also weighing it correctly. And we see, you know, everything is related to repayment plans. So you can't repay my loan, dealing with my lender, need information about my loan, struggling to repay the loan. And you'll see, you know, this is not helping, you know, it's going to, I'm seeing here, worried about, you know, the credit score being affected. Here it is. I picked one here. Late. So, I mean, they're all related to the query in question, right? And they're all very different, but they're similar, right? So that's what's really interesting about this approach. And you know, you can, it's kind of like there's word to vec and there's doc to vec. I don't know if you've heard of these terms. This is more paragraph to vec, right? Maybe we'll make it into a final product where you can take a paragraph and find a similar paragraph by adding extra weighting, by adding all these kind of things. So I'll close this by saying 2 things. And from seeing that the people who, you know, raising their hands, I think we're all kind of on the same page. There are 2 things that are really great right now in natural language processing, in my opinion. I've worked in natural language processing for the past 10 years, and I've seen such a progression. 2 enormous boons to our work is, one is having access to these pre-trained word vectors, right? This is huge. Glove is one. There are tons of other ones. You have them for all major languages, and you'll have them for specialized languages, legal, medical. People have gone through the painstaking work of modeling huge corpuses of different languages and made them available, have released them in the public domain for us to work. So I encourage anybody who needs, unless you need really, really specialized rare dialects or rare technical language, use them. It's probably better than anything we can come up with. These are usually PhD students who work on it. They do it really well. You know, we should leverage that work, and it's there for us to use. The second, so word2vec was definitely a big one, right? But the pre-trained word vectors, even better, right? Because you don't have to do it yourself. And the second thing that was really a real boon to natural language processing is feeding language into convolutional neural networks. Like Priya talked about, it's, CNNs seem to do anything these days, time series, natural language processing, along with, you know, images and sound, these kind of things that it does normally. It does it really well, and a huge advantage is a lot of the feature engineering is done automatically by the neural network. You don't have to worry about it. So, you know, and as we get better at this, it's going to get a lot better than any feature engineering we can come up with as humans. We do have a GitHub. It's not currently open. We were focusing on getting this presentation done. We're going to clean up the code, and then we'll publish every one of these parts, maybe like in 3 separate code bases in this GitHub repository. If you want access, please email us. If you want access before that, please email us. There's also the link to the demo is there. That also will be open for a bit. We may close it after a while. And you have the link to SpringML and Priya's and my email address. So if you have questions about this, it doesn't have to be about case routing or anything natural language processing or even anything CNNs. We love to help out. We love to get involved. If your organization needs help there, we'd also be happy to get involved. So we're going to open it up for questions. If there's any questions, please you can ask them, and we'll be around afterwards as well.